Oh, sorry about the pause there. I had an important phone call I had to take, so we are back at it. And I was talking about exponential decaying functions, and we were looking at the domain and now the range. And the range of an exponential decaying function is the same as the range of an exponential growth function because it still goes from 0, which is the horizontal asymptote, up to infinity. So it is 0 all the way to infinity. The y-intercept, which is this point right here, which is when the x value is 0. Now remember, if I have a number and I raise it to the 0 power, it's always going to be 1. So if I input 0 in for x, I get a y value of 1. That's why it is 0, 1. I do have a horizontal asymptote with exponential functions, and for the parent function is y equals 0. This function is also continuous, just like the growth function. And this function is always decreasing, meaning it's always going down, which is why you use exponential decaying functions when talking about decaying radioactive material and things like that in chemistry. So again, note that the graph of an exponential function is either always increasing or always decreasing. Now, because this is true, it's either always going up or always going down, it passes the horizontal line test. Remember, the vertical line test tells you if a function, if an equation is a function, right? That's the vertical line test. The horizontal line test tells you if that function is 1 to 1. And it's very important that a function is 1 to 1, because if a function is 1 to 1, then we can find its inverse. So it needs to be, so a function needs to be 1 to 1. That's 1 to 1 in order to find its inverse. And that'll be important later on as we move forward with this section. Okay, so exponential functions are 1 to 1, so that we are going to be able to find their inverses. So let's look at a few graphs, shall we? This is the graph e to the x. This is an exponential function, a very common exponential function. For those of you that don't know what e is a number. It's similar to pi in the fact that it is irrational, and e is about 2.718, I believe. About. It goes on forever, that's why it's irrational. So this thing is really saying 2.718 raised to the x, because it is e to the x. Okay. Now, for the parent function, we know that if we input 0 in for x, so if we input 0 in for x, that would be finding f of 0. We get e to the 0, and that's just 1, because any number raised to the 0 power is 1. So it looks like this. And what you learned in the last section is, or in the investigation last week, you learned that if this value, this base, is bigger than 1, it's exponential growth. So we know this thing is growing exponentially, like so. And then it has a horizontal asymptote, so it should look something like this. And if you want to graph it on Desmos, you could. So this is exponential growth. On the other side, this is exponential decay. Now the reason why it is exponential decay is because e to the negative x is the same thing as 1 over e raised to the x. And 1 over e is 1 over 2.718 raised to the x. And what you learned in the last section is that if I have this base that is smaller than 1 raised to a power, that means that I will have exponential decay. So it will have the same y-intercept, but it will be decaying, meaning getting smaller. Okay? Because remember, for exponential rules, if I have x raised to the negative number, it's the same thing as 1 over x to the positive number, which is the same thing as 1 over x to the number. Those are exponential rules. Okay, so here are two very common, these are parent functions. Okay, and they're exponential parent functions. What do I mean by a parent function? A parent function is the most simplified type of that function. For example, this is a parent function. It's the most simplified parabola. This is its transformation. X plus 2 squared minus 7. That's a transformed function of its parent. Okay? This is a parent exponential function. The parent function. This is the parent function transformed. Okay? This is also a parent function. This is the parent function transformed. Okay? So the parent function is just the most simplified part of the function. So the most simplified exponential, the most simplified quadratic, and then the transformed function is what I'm transforming from the parents. Okay, so e to the x is also a parent function because it's a parent exponential function. So we just looked at two types of parent functions. So how can we transform a parent function? Well, a parent function for exponential functions is y equals n to the x, right? And then we have all these coefficients, a, b, c, and d, that could affect the exponential transformation. When we're doing transformations, we do it in the order of CBAD, C, B, A, D, meaning that the order in which you transform your function actually matters. So C, what does C do? Well, C shifts the graph left and right. So this will shift the graph left or right, depending on what C is. Okay. B will be a horizontal stretch or shrink, depending on what B is. A, which is the number in front, would be a vertical stretch or shrink, depending on what A is. And then D shifts the graph up or down, depending on what D is. So each of these values does something different. And when we're talking about transformations, we talk about it in the order of CBAD. C, B, A, D. So first you do C, then you do B, then you do A, then you do D. CBAD. Let's look at some examples. Here is a function. The parent function we are looking at is this guy. And then this is the transform function. So let's talk about C, B, A, D. What is C? Well, C here is 0. There is no C value. B is negative 0.5. A is the value in front of E, which is just a 1 right now. And D is the value out here, which is nothing, called 0. So the only thing that's changing here is the B, because that's the only transformation from this. So what does B do to our graph? Well, it's going to be either a horizontal stretch or a horizontal shrink. Because B is less than 1, this is going to be a horizontal stretch by 0.5, or by 2 actually. So because the way that stretches work, the way that stretches work is this is really negative 1/2, right? And if we're stretching, we're multiplying B by a value, so we're really multiplying it by 2. So you could say by a factor of 2. This is the horizontal stretch by a factor of 2. Now, what does the negative do? Well, the negative is how you get reflections. So, does the negative reflect over the x-axis or the y-axis? Well, because the negative is next to the x value, it's affecting the x values, which means that it's going to be a reflection over the y-axis. So it is a reflection over the y-axis. So we have two things happening here. It'll be a horizontal stretch and a reflection over the y-axis. For part B, we have, let's rewrite this so that it looks a little prettier. Let's put the e in front. So it'd be negative e to the negative 2x plus 1. So let's go through CBAD. C, B, A, D. C here is still 0. B is negative 2. A is negative 1. D is 1. 1. So we do CBAD. C, nothing changes. B is negative 2. So we're looking to figure out, is this a horizontal stretch or a horizontal shrink? Well, because B is bigger than 1, right? 2 is bigger than 1. This is going to be a horizontal shrink by a factor of 1/2. Making a video, and you are now on it. Say hi to Miss Miz. So we have a horizontal shrink by a factor of 1/2. We also have this negative in front, and now the negative is, again, a reflection over the y-axis. So we have a reflection over the y-axis. So that takes care of B. So CBA, A is negative 1. So the 1 doesn't change anything, because in order for us to have a vertical stretch or shrink, it has to be a number different than 1. But the negative sure changes something, and that is a reflection over the x-axis. So that's how you get reflections over the x-axis. And then D is positive 1, so this is a shift up 1 unit. So we have 4 transformations here. 4 transformations. Okay. Now, let's do one more. We're gonna do this one here, C. So this is just e to the x plus 3. Again, my parent function is e to the x. So the only change here is just plus 3. So that's gonna be our first example where we have C, and C here is actually negative 3. And you're like, Mr. Walsh, why is it negative 3? Well, because remember, it's a n to the bx minus c plus d. So because minus c, this is a plus 3. The only way to get this to be a positive is for c to be a negative. So c is negative 3. B is 1, A is 1, and D is 0. So the only transformation here we have is this C. Okay? So this shifting left or right. So the question is, which way does it shift? And because the C value is negative, right, negative 3, x plus 3 is negative 3, it's going to go left 3 units. That's going to be the only change to letter C. So let's go back to these notes. Okay, so we have C, B, A, D. So now that we learned a little bit about C, B, A, and D, let's go back and talk about B. So for B, if the absolute value of B is less than 1, okay, then we get a horizontal stretch, which is what we saw in this example right here, where B was 1/2, and you get a horizontal stretch. If absolute value of B is greater than 1, we get the horizontal shrink. Okay, which is what we saw in this example here. It was a horizontal shrink. Now, when I say by a factor of, you'll notice that I always flipped the fraction, right? 1/2 became 2, 2 became 1/2, because the b value is kind of opposite of what you would think. So 1/2 made it stretch, so I had to make the number bigger than 1, so I reciprocated the fraction. Okay, and then the a value is a little bit different, because if a is bigger than 1, we get a horizontal stretch. Oh, sorry, we get a vertical stretch. And if a is less than 1, we get a vertical shrink. Okay. And then C and D are shifting left and right, up and down. All right. We'll talk more about this in class, and we'll go over some more examples so we can shore up these rules. Okay. I'll see you all soon.